Well, again, thank you, Nick, and thank you all for being here. This is a presentation for our work on retrofit of corroded corrugated metal culverts using glass fiber reinforced polymers. Work done by my PhD student Raul Reddy Shinaredi, who graduated last December, and my co-PI of the project, Dr. Susan Bogas-Holter, and myself from UNM Civil Construction and Environmental Engineering. So we'll give a little background on the topic, our hypothesis, the materials and methods used. We'll give the experimental work we've done and some of the modeling. Then we'll give some about life cycle cost analysis of the system we're suggesting, and we'll wrap up with some conclusions. So the background on the topic, basically, there is a significant level of corrosion happening of metal culverts. Many of those are corrugated metal culverts. That's happening nationwide, actually all over North America. The system has been implemented for those starting using corrugated metal culverts in the 1940s, 50s, 60s. And many of those culverts today, actually even installed 20 years ago, are corroding. Corrosion can result in failure of the road or failure of the culverts or the road above the culverts, resulting in road closure. We've seen this in multiple places, New Mexico included, and a lot of the south and western states. So this is why it's an epidemic problem all over the nation, and there is an interest on finding ways to do the repair or the to stop this corrosion and to extend the life of those culverts. There are a number of existing techniques, including the high-density polyethylene and cure using pipeliners. Sometimes those applications are good if the culvert, the structural, does not have a structural capacity. So basically the structural capacity is offered through other elements. But when the culvert, like the one on the right here, have a need for a structural capacity and to resist strength, the HDPE is not a suitable solution because it doesn't provide the structural stiffness. So the problem, we thought about solving the problem using new type of material that is relatively not new anymore. It's been available and used in structural applications for the last, I would say, 30 years. Still relatively new, used in a few applications, including some reinforcement and for repair of bridges, and for light weight deck bridges. This is basically FRP or fiber reinforced polymers. It's been now used at an increased scale in a lot of civil engineering application. So our idea basically is to use a GFRP slip liner that fits in the dimension of the corroded culvert and slide it inside the corroded metal culvert, and then grout, bumper grout in the annular space between them. The issue is, can we achieve a composite action between the corroded culvert and the new GFRP pipe? And will the GFRP pipe then be able to resist the load, or will it fail at the interface between them? So the new retrofitting system should have, if it works, higher structural capacity and much longer life cycle, because the load now will be resisted by glass fibers. And one of the big advantages of the GFRP system is it is corrosion free. So it does not corrode, it does not lose strength with time or exposure to water. And a lot of the problems happening with the steel ones because of the effect of water and corrosion. So we worked with New Mexico DOT to find a reasonable size diameter that has two things. There is a large number of pipes, as you can see here from New Mexico DOT drawings and papers, but the issue is also we needed to have something that would fit our lab constraints so that we can test it and we can test the capacity within our lab capacity. And our lab can have experimental loads up to 400 kb. So we needed something also we can build size-wise, we can then move and test. So the decision was through working with New Mexico DOT to use an 18-inch diameter corrugated metal pipe that is very similar to what New Mexico DOT is using in many of the current culverts under the highways and under the roads in New Mexico. And that applies to many states, by the way. This is one of the largest diameter used for the corrugated metal pipes. So the materials we used is basically corrugated metal pipe, 18-inch diameter, 90-inch in length, with a thickness of 0.065 of an inch. The pipe it tested in two conditions: in the typical clean and corroded condition, as we have it, and then in corroded condition. We then have GFRP pipes, as you can see here. The pipes are basically made of a fiber layup of different layups of 60 layers of glass fibers. The number of layers and the design of it could be changed based on the condition for the road. These are the ones we used for experimental, but it can be easily designed and manufactured. And they are manufactured by a number of manufacturers in New Mexico and in Arizona and many other states. The pipe we used is 15-inch diameter, 90-inch in length, and have a thickness of 0.41 inch. The GFRP basically is made of glass fiber and epoxy or vinyl ester. Then the last material used is the grout to fill the space. And we came with a grout that's basically an epoxy grout, which is a mix of a two-component epoxy system with aggregate, with a mix of aggregate different sizes at a fineness modulus of 4, that needed to be flowable grout so that we can pump it in the annular space between the pipe, the corrugated pipe, and the GFRP. So one of the things to do in our method is to simulate or mimic the corrosion that is happening in the pipe so that we can test both uncorroded and corroded pipe. So we created a corrosion cell that is basically, as you can see here, a corrosion bath that is including the sodium chloride electrolyte solution, have a potential difference to achieve corrosion in the pipe using a power source, as you see in the schematic, with a cathodic steel plate. The pipe was in the shape that would have been used for directly in the annular space, but we decided to corrode it. And corrosion period we did for 20 years because that's an accelerated corrosion cell. You can see a picture on the right side or top showing inside the pipe where we actually have a nozzle to spray so that we can ensure that that was movable nozzle, so to make sure that the corrosion is spread over the pipe. So this is the pipe shape, and you can see one of the things, by the way, we've done is first we eliminated the because usually on these metal pipes there is a layer or galvanization on the top of it to protect the pipe, despite the fact that it doesn't work that perfect, but we have to remove it before, and that's the sandblasting you see before corrosion, and then you see the corrosion after at the bottom. And this is a corrosion again after 20 days in our accelerated corrosion cell. So we needed to quantify the level or the degree of corrosion. So we took different levels, different cutouts of those pipe, different places, and you can see here different levels from C sub 0 to C sub 4, and we collected them, and then we went and used an ASTM G1 to quantify the level of corrosion. And you can see there is a standard procedure in the ASTM to actually measure the level of corrosion. You can see the 5 specimens we have here, where the mass C0 is the one non-corroded, and you can have we measure basically the corrosion as the loss of mass. And you can see that there is the varying values between -4% to -29% across the pipe, which is close to about 30% of the mass was lost. We went back and took pictures of the corroded pipe, and we distributed this different areas to represent the 5 samples we've taken. And you can see here going from 4% to 29% with image analysis, and we found that the average corrosion is about 20%. And that, by the way, is pretty similar to what you see in a pipe that might have served between 5 to 20, 25 years. Again, the whole thing is a function of the type of the soil. In New Mexico, we have salty soil, so it could come actually, you could see something like this in 10 years. Despite the fact that we might have been using galvanized corrugated metal pipe. The next was to strengthen those pipes, whether corroded or non-corroded, with the glass fiber. So the first thing, we have the pipe that we selected to be a slip and fit glass fiber. We did surface grinding of the glass fiber to improve bond, and roughening the surface after grinding to make sure that the whatever material we're going to add, which is the epoxy grout, would bump. We then washed off to remove all the debris. Here, this is a quick video. You can see the video, correct?
Yes, yeah, we can see the video playing.
Good. So basically you can see sliding the GFRP in. So this is again a limited length, only 90 inch. However, that is the idea. Again, it's very simple, sliding through putting some internal points to allow the sliding. But basically we're sliding the pipe into the metal pipe. You can see here the pipe after sliding, we basically close the ends. And that's going to be exactly the way it would be done on site. We close the end using a thick epoxy and wood. And there are now a gap between the pipe and the corrugated pipe here. Again, we've done testing for both, as you will see in different next slides, this being a corrugated metal pipe or a corroded corrugated. We have two holes so that we can pump from one hole and to get the grout from the other hole. In real applications, there will be a couple of holes in the pipe, and there will be locations where you get the grout out to make sure the whole annular space is filled. This is basically some areas in the pipe, as you can see for the corroded one, was completely lost or cracked to failure. So in this case, similar to what we do here, you will have to repair it using some saturated FRP material. And that's what we did for the case of the corroded pipe. Then we basically mix our grout and mix the grout, fill the material to the polymer. Grout is mixed for about 3-5 minutes. And then the grout is pumped here to the hand pump, where this is used to, and you can see that here, this is the corrugated pipe. You see the students doing the work, filling this with the pump and filling the pump with the grout. And now we fill the whole annular space up to the fact that all the space now between the corrugated pipe and the GFRP pipe is filled with grout. The design for the test was basically coming from the fact that in many occasions, as you can see, there is the culvert pass under the road. But there are cases where the soil settlement could happen, and then therefore the culvert will be spanning. And this is where we have the load concentrated on the culvert, and that can start generating a bending. And that's where we want to make sure, if that happens, that the culvert and the corrugated pipe, the glass fiber and the corrugated pipe are working as one section, and that the force is actually taken by the glass fiber. So we designed the test setup, as you can see here in our lab. This is a 400 kib actuator where we can actually have a displacement control test. At the bottom here, you see this is a support. It is a very large steel beam where it would allow to have at a 400 kib load lower than 0.01 millimeter of deformation. So it's a stiff beam, not moving. We created the supports, as you can see, circular supports here, one as a roller and one as a hinge to actually allow the loading of the pipe as a simply supported. You can see we have used LVDTs at the end to measure the end slip, and we have also LVDTs at the middle to measure the displacement. This is the case for the non-corrugated pipe retrofitted with the GFRP. And this is a very similar test done for the case of the corrugated pipe, also retrofitted with the GFRP, with the LVDTs, with the strain gauges, everything in. And we put strain gauges inside. The strain gauges are placed inside the GFRP because the whole composite section goes in bending. So if the stresses is transferred and the GFRP now is working to take the load, then we should be observing strains in the GFRP. That means the load has transferred completely from the pipe or the corrugated pipe to the glass fiber. That quick bending. we cut the video. The test took about 7 to 8 hours. So this is, and you can see the load displacement there, the load up to 76 kip, and you see the large deformation that is happening. So this is the test for the case for the experimental results, 76 kip, and you can see very large deformation happening, and which means that the new system is still ductile, wouldn't fail at once because again of the bond between the GFRP and the pipe. And you can see basically the failures start usually at the seamless joints with the corrugated metal pipe. Again, here you can see that the failure points where you actually start seeing failure in the GFRP inside the GFRP itself, which means that the stress transferred and actually there is large deformation. And now the GFRP is the element that's taking the load, and up to the point that actually the glass fiber itself fails. And that's where we stop the test here with the loss in capacity. Total deformation 1.8, here was 1.8 inch, but the total is 3.5 inches, you can see. Again, this is a close-up to show you the failure in the glass fiber at the middle, which means complete force transfer between the glass fiber and the steel pipe. And the failure happening actually with the seamless joint of the steel having separation here, and then resulting in failure at this, and then failure in the GFRP. This is again deformed or deflected shape, showing the complete deformation after observing all the load. So the strength is very high, 76 kip is extremely high load. The expected load is in the range of 20 to 24 kip maximum, and the pipe is buried under the ground. So the amount of load reaching to it is way less than that. That confirms that the GFRP can be bonded well to the pipe and can take the load. I repeated the test with the case of the corrugated metal pipe. And you can see again the test, another test that we did it in about 7 hours. And the pipe again at the end, large deformation, similar to the case without the corrosion, and failure very similar to the case without the corrosion. But you can see here the bigger failure happening because of the seamless joint, because of corrosion opening. The capacity, again, similar in the 76 kip, failures happening inside the GFRP. But the main difference is that there's still a lot of capacity here, but there is a considerable loss of capacity in the case of corroded pipe because of the seamless joint. Pictures here just showing failure of the GFRP in that case as well, which means full load transfer, and the fact that the pipe is corroded did not make any issue on the load transfer with the grout. This is the thermal picture showing that actually the opening is very large in the case of corroded pipe, and you can actually see now the GFRP and the grout being cracked into it. So that would be the key point in this, that we got to have enough strength at the seamless, at the joint. This is the deflected shape. Again, you can see a very ductile system with adding the GFRP to the corroded pipe. By the way, if you see some of the field pictures of this, you will see right away that there is very large deformation up to that the road, as we've seen, could fail. Comparison between the two, that is the load deformation or deflection of the non-corroded pipe and the corroded pipe. Very similar behaviors. So the GFRP basically can take the load and can completely be integrated with the system, whether the pipe is corroded or non-corroded. We look at the strain. How is the strain? The strain is important for us because it tells us if there is a load transfer or not. And you can see the strain in the case of non-corroded and the strain in the case of corroded. So there is a complete strain compatibility across the system up to the low failure load, which is 75 kip, which means basically that the epoxy grout used enabled developing a complete composite action. We did finite element modeling of the system to simulate the failure and to understand the progressive failure that is happening in the tension and the compression, and we to basically understand what is happening there. And the finite element model is a comparison to the experimental work is here. And what the finite element model showed us basically is that main issue is the joint, and the fact that the joint actually would lead always to the final failure of the load because of the way that this joint in the GFRP, in the corrugated pipes is developed. But again, as I've shown, that the load capacity is in the 70 kib capacity, which is very high load compared to this pipe. We also did quickly a life cycle cost analysis to see what is really going to be the value if this system is used. And we considered both the production cost, use cost, and demolition cost. We compared to current technology, like the current, this is the cost for the current corrugated metal pipe, the high density polyethylene system that's available in the market, and the GFRP. And you can see that the GFRP is higher cost compared to the system. But I also need to remind that we could reduce the cost of the GFRP by changing the thickness. We used a significantly large thickness, and that resulted in a capacity we might not be in need for. So the GFRP could be reduced, designed, and got at a smaller thickness, which could reduce the cost as well. We did the life cost analysis, assuming initial cost for the retrofit, annual cost for maintenance, cost of retrofit of replacement if needed, and basically that's a system, the typical. So basically, if you have here, then you have, if you completely change the system, you will have to replace it after 25 years, retrofit another 50, and then replace again and to the end. We use this economic model to basically calculate the life cycle cost. And the main difference is for the CMP, again, you would have to use this. You got to replace it every 25 years or retrofit it, compared to the case for HDPE, where you can actually replace it in 50 years because it could take longer life in use. So we calculated the life cycle cost for 100 years for the current corrugated metal pipes with no, basically with no replacement or no GFRP, or with the use of HDPE for retrofit. We also did it for the case of glass fiber. To be fair, we did glass fiber twice. We did it similar to the 50 years. However, we understand from reality is that the life cycle for a glass fiber is close to 100 years. It does not have, it have much higher capacity and stiffness compared to the HDPE. And from environmental points, it does not need to be replaced for up to 100 years. So we did the calculation for the glass fiber case for 100 years as well. So when you compare the case for 25 years for CMB, because every 25 years, basically you need to do a retrofit or replacement, compared to the cost for HDPE, which is 50-year replacement, compared or retrofit, compared to GFRP, assuming 50 years, you will find that the cost on the life cycle based analysis of both this current system, HDPE and GFRP, is very similar. However, if you actually take GFRP to its capacity, which is 100 years, you will find that the life cycle cost would show you that the cost for GFRP will be significantly lower than the current system that's being used. So in conclusion, GFRP slip liners are suggested for structural retrofit of existing corrugated corrugated metal culverts. Design can be conservatively performed using ASH2 guidelines and can help us in determining the thickness. And that's the extension of the work we are doing now for developing guidelines to do the design. Experimental investigation showed that the behavior of corroded and non-corroded retrofit pipes were similar and exhibited very high ductility when GFRP was used for retrofit. The GFRP retrofitted pipes exhibited excellent composite action. Bond was intact until failure for both corroded and non-corroded pipes. Validated finite element showed that the criticality in design of the system is the seam joint that is controlling basically the behavior of the retrofitted corroded metal pipes, which can be taken into account in design. A life cycle cost analysis comparison indicated that for 50-year service, GFRP method has lower or equivalent cost to the current available methods of the low density polyethylene or high density polyethylene. I would like to acknowledge of course, those students who do the work and are already who finished this PhD, and all the my team members who actually helped in doing this work. I'd like to acknowledge the funding by New Mexico Department of Transportation and by Tran-SET, and also by Seaway Shield Composites, who donated to us the GFRP pipe and worked with us in a lot of parts of the system. And that concludes my presentation. I'm ready for any questions.
Great, thank you very much, Mahmoud. If we have a couple minutes for questions, so if anybody has any questions.
Yes, I have a question about the pipe. You can see when you do the composite pipe, the material pipes, the new problem coming is for the connection. What is the plan for the connection between the composite tube?
You
pipe?
mean the seam joint? Is that the question?
Yes. If the two parts connect together, if we have two pipes.
I see. There is a standard connection. There is standard connections to actually make longer pipes, very standard that has a thickening, and they actually are using those pipes a lot in manholes retrofit. So there is standard connection where you increase the thickness, the diameter of the pipe a little bit, and make a bigger pipe, and then you insert the other pipe in it. So standard. So good question. It's related to, I would believe, to the fact that if you need to retrofit a very long culvert where you wouldn't have one pipe for it. So very standard, and the strength is not governed by the connection.
Okay, thank you.
Sure.
This is Farshad Omedwar. I'm one of the engineers in Albuquerque working with WSP USA. I was just wondering, for the liner, do you have to have enough grout at the bottom of the pipe? Do you just set the liner in the pipe, or do you have to keep it up so that there is enough clearance centered on the existing pipe so there is enough clearance for the grout to go all around?
Good question. So what is happening is, again, depends on the design, yes? For testing, we centered it, yeah? And when we were doing testing. But in reality, you do not have to center it. You can have it in what we've seen from testing. If it's centered, again, we have 18-inch and we have a 15-inch pipe. So we have something about, I would say, given the thickness, about an inch top and bottom. And that was enough to actually bump the grout. If you need to reduce that in one side and increase it on the other, I don't see any problem because the bond is very high and the material, the grout strength is in the 7,000-8,000 psi. So there is no problem if you don't center it necessarily.
Okay, thank you.
Sure.
Are there any other questions for Mahmoud? Great. Well, if there's no other questions, I guess we can finish up a few minutes early here.